So let's take a look at the definition of a relation. Now, a relation on a set X is going to be a subset of the set of pairs of elements from X. That is, R is a subset of X cross X. Now, if this notation doesn't mean anything to you, an example will help clear it up. Suppose, for example, that X is equal to the set ABC. So it's three elements. These might be three objects of choice, three candidates in an election, what have you. The set of ordered pairs, the set of all pairs of elements from X, is denoted X cross X. So this is going to be the set of all ways of pairing up elements in X with other elements in X. So for example, we can pair A up with itself, A up with B, A up with C. Then we can pair B up with A, B up with itself, and B up with C. And finally, C can be paired up with A, C can be paired up with B, and C can be paired up with itself. So X cross X, that's just the set of all ways of pairing up elements in X with other elements in X. And we say that a relation is a subset of X cross X. So a relation just identifies some of the pairs from the cross product of X with itself. So for example, we might have R is equal to the pair AB, AA, and say CB. So the relation identifies, in this case, three pairs, the pair AB, the pair AA, and the pair CB, and sets those aside and distinguishes those. So that's what a relation is. A relation is just simply a subset of the cross product of X with itself. An important piece of notation, we will write A is related to B just in case the pair AB is actually an element of R, is an element of the relation R. So for example, in this relation here, this relation R here, we might write A is related to B, but B is not related to A. And why is that? Well, B is not related to A because the pair the pair BA is not an element of R. It's not one of the pairs identified by this relation R. So that's the general definition of what a relation is. Now, in general, we're not going to be interested in any subset of pairs of elements from X, but rather subsets that satisfy certain very natural properties. The first property is reflexivity. Reflexivity says for any element A in X, A has to be related to itself. So the pair AA has to be identified by the relation R. Another property, completeness. Completeness says for any two elements of X, A and B, either A is related to B, B is related to A, or A is actually equal to B. So you can think of completeness as being a generalization of reflexivity. Reflexivity says for every element of X, that element has to be related to itself. Completeness generalizes that and says for any two elements of X, there has to be some relationship between those two elements. Now, transitivity says for any three elements, A, B, and C, if A is related to B and B is related to C, then A has to be related to C. So to think of a concrete example, think of numbers on the number line and the relation less than or equal to. So if we have our number line here, and we have one number, let's say A, and I know that A is less than or equal to B, and I also know that B is less than or equal to C, so B is to the left of C, then it has to be the case that A is to the left of C. So if on the number line A is to the left of B and B is to the left of C, then A has to be to the left of C. So that's transitivity. Another natural property is symmetry. For any pair of elements from X, A and B, if A is related to B, then B is related to A. So if A can see B, if A and B are people, if A can see B, then under normal circumstances, B can also see A. And finally, we have asymmetry, which says for all pairs A and B, if A can see B, then it's not the case that B can see A. So you're looking through a one-way mirror or something like that. So symmetry and asymmetry, they're not complements of each other. They're two separate properties. Finally, let's look at an example. Suppose X contains 4 elements, A, B, C, and D. And here are two relations, R1 and R2 on X. So I've identified special pairs of elements from X. Note that R1 is reflexive because R1 contains the pairs AA, BB, CC, and DD. To visualize what R1 looks like, I'm going to draw an arrow between two elements of X if the pair AB is in R1. So for example, I'll draw an arrow from A to B because the pair AB is an element of R1. Since BA is an element of R1, we have an arrow connecting both A can see B and B can see A. Note that B is related to C and A is related to C, but C cannot, we don't have any pair CA or CB in R1. And finally, we have D, which is not related to any of A, B, or C. Since it's reflexive, we need to add these reflexive arrows. So this is a useful way to visualize this relation R1, this graph right here. So we see that R1 is not complete because, for example, there's a pair of elements, namely B and D, such that there's no relationship between B and D. Neither BD is in R1 nor DB is in R1. What about R2? So R2, we have A is related to C, C is related to B. So we also have A is related to B. B is related to D. So we get C is related to D. And finally, A is related to D. So R2 represents a situation in which there's a linear ordering. A is related to C, which is related to B, which is related to D. And those orderings are strict, meaning that A is related to C, but C is not related to A. So here are two examples of relations. And it turns out that relations are a very important tool that have been used by mathematicians, computer scientists, philosophers, economists. So it's important that you understand these basic definitions and how to visualize and understand what relations are.